presentation, please. Perfect. Okay, do we want to maximize this? Perfect. Okay, I'm going to skip forward. Okay, so, well, actually, I'll just remind everybody the outline of this talk. So we've talked about an investigation of autocorrelation in recruitment. And this morning, we're going to talk about definitions of overfished and depleted, a definition of overfishing, and then an update on the process to adopt a harvest strategy policy. And I guess there's one last bullet, and that's just sort of the MSc program of work for next year's thoughts that I have on that. Okay. So the SRB made a recommendation, which I really like, and that's the Secretary Commission adopt an absolute biomass limit defining depleted to avoid low biomass limits or levels where stock dynamics are poorly understood, such that recovery projections would be unreliable. I think that's a well-worded recommendation, and I thought this is something that I'm very interested in working on. So to actually define a depleted point, that's not an easy task because hopefully we've never been there. And so we thought, well, there's two ways to do this. One, we could use the lowest spawning biomass observed in the estimated historical time series and see if that sheds any light on biomasses we'd want to avoid or percentages of some biomass we want to avoid. And number two, we could use a sort of worst case scenario simulations to determine at what spawning biomass level the population may not recover. So use our best understanding of the dynamics, put in some worst case stuff, which I'll show you, and see, okay, if the biomass gets to this level, it won't recover even without any fishing. So first, this is a plot and a description that we've been working on to define these different concepts. And this is a work in progress, something that I realize I need to practice and get better at. And we need to improve the colors on these plots as well. But this is what we're trying to communicate to commission stakeholders and the public about these different concepts. So on the left is the absolute spawning biomass, and the solid lines are estimated lines from the stock assessment work. And so the red line with fishing is our best estimate of the current stock spawning biomass and historical spawning biomass. And so you can see it was high in the late 90s and then subsequently decreased with a few bumps to 2025 around just under 200 million pounds, I believe it is. And this is the median from the ensemble from all four models. The blue line on the left plot is the estimated spawning biomass if fishing had never occurred on the Pacific halibut stock. So that's the dynamic unfished spawning biomass. And what's interesting about that, it shows that the spawning biomass would have decreased without fishing due to various conditions, call those environmental ecosystem conditions, whatever they are. And those, the decline in the spawning biomass from about 2000 in the unfished estimate is mostly due to lower recruitment and smaller size at age. And we saw that in some of the simulations I did at the last SRB meeting. So in my mind, it looks like commission decisions in the last 15 years or so have actually halted the decline of the spawning biomass a little bit compared to the decline that it would have had without fishing anyways. On this plot are also plotted two reference points. One reference point is our overfished level, which is 20% of the unfished value. And so that's the overfished dashed line. And because the unfished value is changing, is dynamic over time, the overfished level also changes over time in terms of absolute spawning biomass. What we're looking at today is a depleted concept, which is an absolute constant spawning biomass. And we've just plotted an example level of depleted. I think it's 70 million pounds on this plot. And you'll see why I did that later. But that is showing that the depleted level is a constant value of spawning biomass that we would want to avoid going below. So then if we take and translate that to a relative spawning biomass, which is taking the red line on the left plot, dividing that by the blue line to get relative spawning biomass, we can actually have uncertainty for that one, which we've plotted. We can then translate these two reference points of overfished and depleted onto relative spawning biomass, because overfished is defined as 20% relative spawning biomass. That's now a constant at 0.2. And then the depleted is a dynamic concept in terms of relative spawning biomass. And you can see there may be a case where depleted is greater than overfished, or vice versa. So we'll work on communicating that and how to best communicate that to stakeholders, and any advice you may have would be greatly appreciated, because the SRB has been a big help in communication in the past.
That's interesting. And the way the depleted changes to dynamic when it's relative.
Yeah, so that was something too. Ian and I were discussing this, and we started plotting it out. We're like, this is a concept that we really want to understand more and communicate this a little bit.
That is interesting.
And some of the questions we've already received from commissioners when I've given a trial presentation of this were, well, could overfished and depleted actually swap? And so I want to understand better, when would that occur? What are the cases when those two things, when you could be depleted but not overfished, versus you could be overfished but not depleted? So I think some work on that would be interesting.
Yeah, I think you probably have to it's kind of a different number, right?
Yeah.
The depleted is different on the different plots, so it's almost like relative sense.
Well, and yeah, so yeah.
I really like this. I think it's novel, but useful.
Yeah.
Because you have that relative spawning biomass approach here for reference points. It really helps to have both overfished and depleted and defined.
I like it too. And yeah, I completely agree with you. I think this is work that I think would be important for all fisheries going forward.
Because the argument has always been, we can't use dynamic B0 because you'll fish the stock to nothing. Now that you have depleted on there, you can see your depleted's going up. So there is an indication, right, that something is going on.
Yeah. And to my mind, it's really trying to separate, or trying to not separate, but understand the effects of fishing and the effects of the environment / ecosystem. And when do you take management action for the effect of fishing? And when do you take management action for the combination of those two effects? The depleted concept is really your safety net. And so the question that we have now is, what is an appropriate level of depleted? That's not an easy question.
That's one. And the other is going to be probability. Eventually will be just find something.
Yeah.
Something to it.
All right, so so let's look at the two methods that we proposed. First, the lowest observed spawning biomass. Using this type of concept to determine depleted is nice, rather than saying 70 million pounds or something like that. Because as we update the dynamics of our understanding of the dynamics of the Pacific halibut stock, we may change the scale of this population. We've seen that with changes in M and things like that. Defining it based on an estimated value actually automatically scales it with our best understanding of the dynamics. The problem here is that in the 70s, the biomass is estimated to be quite low in one of the models, the coastwide long, but there's a lot of uncertainty about that as well. The areas as fleets model isn't quite as low. There's a lot of uncertainty around that. But in the more recent years, we see we're close to low levels that could be similar to the 70s or lower or higher. So we're not certain about that. But we have more certainty about where we are now than where we were in the 70s. So our thought is, well, because we have more certainty, maybe we could use a recent lowest spawning biomass, which actually is estimated to have occurred in 2024. But the question then becomes, how does the threshold relate to that value? We're already there. I'm certain the stock could recover from where we're at right now. We've seen signs of potential recovery. So what do we define that as? 50% of where we're at? What is the value? So that's where the challenge comes from. So what we wanted to do is, well, using that has its benefits, but also its challenges. So what we thought, well, let's do some simulations to determine can we find a threshold where the stock just has a low probability of recovering? And so what we decided to do is, well, let's use a worst case scenario, project at a high fishing rate for 40 years, bring the stock to low levels, stop fishing, project for another 50 years, and then see how the stock recovers. And we didn't actually fully stop fishing after 40 years. We allowed 3 million pounds of more fishing mortality just due to subsistence and bycatch and other things, just to be a little more realistic. What is a worst case scenario? Well, it's a low weighted age, our current weighted age that we've been observing. It's low average recruitment, so using the low PDO for these simulations. And then it's introducing the depensation that we evaluated last year, I think it was, but we've introduced a depensation parameter of the value of 5, which was within the range of what we investigated and we found in the possibility, but it's at the high end of depensation. So I've shown you the plots of the stock recruitment here with the different levels of depensation. And you can see that with a depensation parameter of 5, that, there's going to be very low recruitment at low biomasses. So this is a worst case scenario. We thought, okay, let's do simulations and see what happens. We summarized the results on the left. So we did 500 simulated trajectories. And then all those trajectories didn't go to the same value when they stopped fishing, that it was a range of spawning biomasses because it's a random simulation. But then we decided to summarize of all of the trajectories that continued to decline, so did not recover, what was the spawning biomass after 40 years of fishing? And then of the trajectories that did recover, what was the spawning biomass after 40 years of fishing? What was the lowest spawning biomass level observed? And you can see that there is overlap here, but there does appear to be around that 70 million pound mark that, there were only 3 or more that didn't recover. And at a 90 million pound, all trajectories recovered. So we're trying to identify that threshold. Another way to present this was to look at the proportion of trajectories that did recover at an interval of spawning biomass shown along the horizontal axis here. So if the spawning biomass was basically below 40 million pounds, none of those trajectories were able to recover. If it was between about 40 million and 70 million pounds, less than 50% of the trajectories would recover. And then once it was above about 70 million pounds, about 50%. And then once it was above, I guess it's above 85 million pounds, all trajectories did recover at that point.
Oh, and how does this match with the inflection point?
That in a decompensation curve. Yeah, I thought about that. I looked at it and now I can't remember. But you're exactly right. This could be dependent on that inflection curve. I had that thought. I can't remember.
Was it in the figure or were the figures relative?
The figure
Yeah,
did, yeah, because yeah,
I mean, essentially you want to know when it goes below the replacement line.
it wasn't, if I remember right, it wasn't as clear. Like I thought, oh, this is just totally that point, but it wasn't quite that. There was a little bit, there was a different value. And I think this inflection point was less than, you know, that point around there was less than 99 pounds or 79 pounds. So there was some effect here. But I can certainly look into that. Or I could do different depensation parameters and try and see how the results.
Yeah, probabilistically still not recovering.
Yeah.
It
Yeah.
should come from the second derivative.
From the what? The,
Second derivative.
oh, right. Yeah.
This
Uh,
relationship or?
Spawning stock biomass when when the first derivative, when it turns from increasing to decreasing zero, when it turns to convex to concave, the second derivative is zero.
So that's the inflection.
Yeah.
Yeah. And actually, my group has derived a formula calculating that, so
Okay.
it's quite easy.
From a Ricker or Beverden pool. From a Ricker or Beverden pool.
Think about a silo load, and because that's the extended curve, and then the sigmoid of Beverden pool.
Functionally, though, that would interact with recruitment variability, so there would be some, wouldn't be right on the analytic solution because it's not deterministic recruitment, right?
Yeah,
Slightly different.
but something is happening around that point.
Yeah. For
The
sure.
recursion autocorrelation should matter. Probably
Yeah,
getting down to that point. The sequence of negative recruitments.
And then getting out.
Everything
Yeah.
out, you're in a low recruitment regime.
Yeah. So yeah, that's a good point. We did not have any sort of autocorrelation in simulations as well. But in defining this worst case scenario, it's a worst case scenario. So it's definitely,
Worst case, I'd say.
yeah. So it's a
You can say it
conservative.
would be the worst case.
Yeah.
This is the worst of the worst.
Yeah. And so, but I found that interesting because, you know, we're sitting here looking for a threshold, and this is actually a conservative threshold that's quite below where we're currently at. I mean, we're currently about 170 million pounds, and we're talking 70, 90 million pound threshold in a worst case scenario. So yeah, it's very encouraging. And I thought, okay, that helps me sleep at night. So, but you know, so we're just curious, like, is this sort of method of something that we should be exploring to help us identify a threshold for a depleted state? In these simulations, we're suggesting a threshold of possibly 70 or 90 pounds, which is why I think we plotted 70 million pounds in that plot earlier. And so yeah, that's what we have right now on investigating a threshold for depleted. One, the lowest spawning biomass we've observed is right now potentially in the 70s due to uncertainty. But how do we then define the threshold based on the lowest spawning biomass we've observed? And then the second method of using simulations of a worst case scenario.
So this would have to be updated every operating month,
That's, yeah, it would,
which is fine.
Yeah. it would change, potentially change with different understanding of the dynamic. And that depensation parameter of 5 did come from the analysis last year, where there were a few cases where 5 was potentially within the range of estimated uncertainty. Could have shown that. But
Yeah, that's the point
Like
where I'm
large.
still,
yeah,
that's the point where I'm still a little unsure. I mean, you guys do such a great job of putting things in a probabilistic framework that this feels like a departure from that. And I wonder if you could choose a value that corresponds to like the 90th percentile. But I know you've got different scenarios of 90th percentile of which
Yeah.
scenario.
Yeah, I wanted to do that. The challenge was when we looked at depensation, we looked at it in the different models from the stock assessment and the estimates of recruitment. Can't remember the details, but depending what data, estimated data from the stock assessment you used, you would get a wide range of depensation. Some of them didn't even converge. Some of them would have just an uncertainty between 0.5 to 15, right? That was the uncertainty range. So there was no data really informing it because we hadn't been down to a low enough leading mass to inform the curvature of the depensation. So when we looked at it, we couldn't really put it into that probabilistic framework because we didn't have a good confidence interval that we really trusted. One model I remember said, "Oh yeah, it's actually this is good. It's confidence interval 0.9 to 2 or something." And then the next model, it's 3 to 10. So it's a challenge to do that. So we took a look at sort of all of it. Just said 5 is probably at the high end of what this would be. It could potentially be.
So it's probably conservatively, super conservative.
Yeah.
90, 100 million pounds. What would roughly a TCUI be at that point?
Well, it without a harvest control rule. So they would depend on if the harvest control, but without a harvest control rule, I mean, the TCUI would be, I imagine 10 to 20 million.
Yeah, be half what it is right now.
Yeah.
Basically. At least half, because you presumably have some kind of ramp.
Yeah, I mean, the harvest
Well,
control
we said
rule would
without
shut it
the
down. Yeah.
With the control. It would depend on where the
On the
fish was. So if we were at a low,
Relative spawning biomass.
Like if you're approaching that, your harvest rate's going down and the stock's going down. So even that 3 million pounds, I mean, that might.
but if we were in really good weighted age and really good recruitment, we would be overfished long before we got near this.
Yeah.
Because the productivity of the stock was. So if you had to go back to the late 1990s, the control rule would be ramping us down way before.
Yeah, the control rule would shut off fishing before we got to this level. But it's now you see the depleted level and the overfished level are around similar relative spawning biomasses. And so that control rule is, you could potentially have fishing at a depleted state.
So this number you picked for this plot is close to this 70, 80 million.
Yeah, I created the plot after I did the analysis, so. Yeah. But it's interesting. And so I think there's a number of things to do with depleted is I look forward to your recommendations on methods or ways to determine a threshold. But I think as Sean was saying, well, choose a threshold, then you have other things to do as well. You have probabilities, what sort of probability do you want to state in exceeding that threshold? Are you at the median? Is it you want to be even more conservative? But then further beyond that is what do you do when you are approaching a depleted state? So do we do we start investigating harvest control rules that are related to depleted as well as to overfish? Do we have 2 harvest control rules? How do we do that? And I think that's sort of the next things that I want to investigate once we come up with a threshold for depleted. So that's what I have on depleted at this point in time.
Can we just go back to that? last-
Oh, sorry, the over this one here.
Yeah, just trying to like see what a scenario might be like. So let's say we're looking at the one on the right. You've got the blue is the probability distribution for relative spawning.
Mhm.
Let's say it was just slightly lower, so that depleted was now in it.
Mhm.
So the question is like, when do you react?
Exactly.
What
And so-
are the drivers that, because that's unfished.
Well, this blue line on this side is fish divided by the unfished. So the drivers in the relative spawning biomass in this context is only the fishing. So that the relative spawning biomass on the right here is removing. It's only determining the reduction in the stock due to fishing. But when you bring in the depleted line, that's now bringing back in the environment and the fishing. It's yeah,
So
super interesting.
like if you had this in a decision table now you could say, what is the probability next year or 3 years, whatever your projection is, that this is not going to complete?
And overfished.
Yes.
Separate probably, what is the probability? So here's what's completed and they're kind of converging. This particular point doesn't can differ a lot.
Right.
So it's almost like, you check the first condition and you check the second condition.
Mhm.
Really need to take action, right? If both of them, high, whatever that probability is. So what were we talking about yesterday? We were looking at probability of greater than 5% decline. Numbers were in the, like you were projecting a 30% chance. It's up to like 70% chance, greater than 5% decline. That's where it's getting pretty good.
Around 120.
Yeah. And then that's compared to the current spawning biomass, which could be much higher than this. But the decision table does also include the reference points, include the 20%.
Right.
And the probability of being below 20% in 1, 2, or 3 years.
So something to think about in terms of probabilistic, when you create the decision table, the reason there's no variance on the left is because you can't show the variance independently. Because with and without fishing have covariance. So we can plot the ratio,
Uh-huh.
but plotting the two variances independently is not accurate. So that's why you only see the variance on the right-hand side. But the converse of that is that the depleted value on the left has a variance, and the spawning biomass on the left with fishing has a variance. And it would be the overlap of those that would give you the ratio for the, so the decision table calculations would be separated. In one case, it's the ratio on the right for the overfished. And in the other case, it's the ratio, but it's a different ratio. It's now the ratio of with fishing, if the spawning biomass with fishing to the depleted estimate with whatever variance we have on that. And that maybe that's an external quantity that comes in without any variance. But that's something to think about, the calculations. It's frustrating because people often look at the plot on the left and want to see the variance, but you can't do it because there's covariance. You have to look at the ratio to get the variance. Right?
Yeah. But yeah, I think some thought about management action as you approach these thresholds. I like what you said, Sean. So there's really there's 4 cases. One, you're above both of these thresholds and you're fine. You're just doing management procedure as normal. You're below overfished. Well, and then the control rule, or you're approaching overfished, the control rule is going to come in our 30-20, which is currently what it is. You could be approaching depleted, but not approaching overfished in an odd case. And then maybe a different control rule, whatever that is. But then what about that case where you're approaching overfished and approaching depleted? Do you have an even more extreme management action to come into there? So
I mean, that's in some ways the sort of positive case for management. It means that you're approaching depleted, which is bad, but your ability to lever your control is relatively strong.
That's
because
true.
It's largely from fishing.
Yeah. Yeah.
It's the harder ones are where you're not even close to overfished, but you're getting close to depleted. Where
you don't have the lever.
you gotta look.
Yeah, that's a good point. So yeah, any recommendations on simulations we could do, and things we can look at to help define this? At this point in time, we are showing a worst case scenario, very conservative, that we're probably quite a ways above the depleted, a potential depleted level, where I think the SRB phrased it as low biomass levels where stock dynamics are poorly understood, such that recovery projections would be unreliable. And so that's the way we've been trying to think about this.
This fits that definition.
Yeah. Yeah. And so that's the work that we've done so far.
Yeah, I'm not sure if this should just stand on its own. You could do more simulation. Create some see and stuff, but if you're not projecting conditions that could behave that way, I mean, that's all you don't understand is you've approximated a position where, yeah, well, maybe that's where it ends.
And we define a concept of depleted, and we're just aware of dividing. Maybe we define a threshold, and then it's just a value that's reported to the commission, and there's no specific management procedure.
Like trigger in exceptional circumstances.
Yeah.
Dig into it.
Yeah.
Maybe now you have to go back and rerun projections using this story model.
Yeah, because really the way we would get to depleted, I think that the control rule is so aggressive that if we're below 30%, the MSE simulations show there's very little chance of getting to an overfished level of 20%. Because that control rule just backs off the fishing so quickly. Without the control rule, you can get to low relative spawning biomass levels. But that is a good point. I think having the depleted threshold would be nice to report for the MSE, and just say, what is the probability of approaching this threshold? And I think we'll find in the simulations as they currently are, it's a very small probability as well. The thing to be aware of, and I like the exceptional circumstance concept, is that if the environmental or ecosystem conditions change such that it continues to drive the stock down to lower levels, which are outside of the MSE simulations right now, that's when we would want to say, okay, we're obviously going to a level that is not being simulated. Let's call an exceptional circumstance and figure this out.
Can we go to the next slide again?
Yeah. This is the spawning biomass.
Sorry, the results slide.
Okay.
Yeah, I just want to quibble a bit about where you called the threshold.
Yeah.
So you called it at 70 million pounds.
Ian and I quibbled a little too. So.
I mean, 70 million pounds looks fairly arbitrary here, and it seems like, what is it, like 85, maybe where you'd have to set it to have essentially within the simulations no probability of no recovery.
Yeah, and that was Ian's argument as well. I was thinking of, okay, where's about a 50% probability of recovery, but that might not be the right way to do this depleted.
50% probability of having no help in
Yeah.
the future.
Yeah, not probably a good.
Under a worst case scenario.
Yeah, under worst case. Yeah.
So you're suggesting use the 100% as
Yeah.
Mhm.
lowest biomass of which is 100% chance of recovery, which
Yeah.
makes sense because you want things happening before the probability starts going down.
And that gets to a question that came up at the work meeting, which was if we were to have a definition of depleted, would we need some kind of buffer around that definition or not? It depends on how you calculate it.
Yeah.
If you calculate it as a 50th percentile, then you'd want a buffer. But if you calculate it as the 95th or the 100th percentile, then obviously, right.
There's buffers on buffers. And at this point, you're using, the worst of the worst case scenario. There's
So
Yeah.
that's kind of what
But in that case, I would pick 85 instead of 70.
And what I would like to do, I mean, you can tell that there's obviously Monte Carlo error in here. There's not enough simulations to really, this should be a pretty smooth curve. So I would probably embark on more simulations to smooth that out and really get a good idea of that. So it sounds like one, the worst case scenario, depensation is obviously high value, but that's, a worst case scenario. We would define the worst of the worst case scenarios by tacking on low recruitment and low weighted age, but that low weighted age is also the low weighted age that we've observed in the time series. Could it go lower? We haven't seen that, but that's worst case scenario. We've done the simulations, probably more would be helpful. Defining a threshold based on 100% probability of recovery, and then potentially using this concept of depleted, what is management action? Maybe something to report. What's the probability of being below a depleted state? And then maybe using it to define an exceptional circumstance, which is sort of some of the things that I've heard.
Yeah, I mean, with non-stationary dynamics, the idea of choosing a point in the past as the worst case scenario is well, certainly.
Yeah. I think
This isn't worst case in all dimensions.
yes. I think having a look at the lowest spawning biomass we've observed, especially when it's right now, is useful for people to understand because one, I think many people aren't happy with where we're at right now. Maybe that could be a threshold for another concept. But we've been working on that as well.
You have to be in some other term. That's what we're getting at with the CPUE analysis. Is tries to define it in terms that they're thinking of rather than SSP targeting.
Yeah. Just want to go out and catch a fish. Yeah, and then I've had conversations with stakeholders that like, well, this spawning biomass is fine for some, where we are successful, but others are not successful. So there's a real diversity ability.
So imagine particularly between the rec and commercial sectors.
Yes.
They're really different targets.
And also for the same amount of spawning biomass, the way it's distributed across areas will create very. It's good.
True.
So in the spirit of communication, we're on a thread here that we started quite a while. You could convert this to a fishery CPUE equivalent into FIS. So at least now you have, what does, what does 85 million pounds mean to?
I like that. It means like catch rates would be even in the best places like they are right now. It's some arbitrary, undesirable place.
Yeah. Could even do it by regulatory area. Models we saw yesterday.
It's not a one-to-one because local citizen and fishery access a lot of.
That's fine. It's just whatever it is. To see what their equivalents.
But it's not gonna, there isn't gonna be one there's gonna be a range of values depending on the demographics that are in stock right now. You could have a pretty big range of CPUE for the same spawning biomass if you have incoming recruits versus recruits.
But it would be interesting.
But you could certainly envelope that.
Yeah, if the age composition looks like it does now. without- Following up on communication, how much discussion have you had about decompensation in general? Is that a concept that they have been exposed to, or is this going to be sort of starting from scratch? What does decompensation mean? Why do we think it's worth modeling here?
There, with the analysis we did last year, some exposure, not certain how well it's been received, but it's a conversation. It's something we'd have to explain every time we bring it in. But I think when I explain it as, the reduced recruitment at, very low spawning biomasses, I haven't had many questions on it. Been surprised.
That means you don't get it.
Yeah,
Why?
it totally just goes over their head, but yeah,
I think it's most easily explainable in terms of like finding mates, right? You're
right.
down to the
Yeah.
point where there's a way to, it exists at some point, right?
Yeah.
You've got 2 males and they're both Neolitians, 10 females and they're both down
Actually, the perception
2A.
is that there's a stronger stock recruit relationship than there really is. I think people would like to believe that
Yes, exactly.
if you add spawning biomass, you get more recruits, and that's actually not what we see. Time series, we see that recruitment's generally environmentally driven across the range that we observed. So this is really talking about a relationship that they expect to be there, but not at the biomass that we've actually been operating. So it's going to be easy and hard to explain.
Yeah, certainly work on that.
I mean, we saw coming out of the 1970s, which may have been a very low period of stock biomass. The recruitment started before the spawning biomass caught up. It was not a case of we had more biomass and we got more recruitments. It was the opposite. Environment changed, we got more recruitment, and then that later turned into more biomass. Yeah.
It's the hooks and loops. Carl's old hooks and loops.
Yeah. All right.
Yeah, you may need like a cartoon. Some scenarios where because there's finding mates, there's also like triggers, aren't there? Like if they won't mature under certain conditions. I think some houses where and some invertebrates are like that.
Those mechanisms are harder to explain.
Yeah.
So it's worth maybe just focusing on units.
Yeah,
And
yeah.
then say that there are other mechanisms that would drive this. But in the extreme, you got so few that they can't find each other.
Yeah, and most people can understand that.
We probably most men working in Alaska can understand that.
Yeah. So I've heard. All right, are we ready to move on to overfishing? Okay. Okay, this one I think will be a little bit easier. The SRB recommended that we evaluate via simulation the ability to detect overfishing in the MSE. And just an update on this, these simulations have not been completed, and thinking about it, right now we just need a more realistic estimation model in the MSE process, where the estimation model right now is just using a random draw from a bivariate distribution. So it doesn't actually have an estimation model in it. So what I've done is I've started writing an estimation model in RTMB because I want to learn that. I want to see how that compares and see if I can develop a really simple, quick estimation model that I can insert to the MSE. This has been something that's been on the to-do list for 5 or 6 years.
try Sam's new hybrid delay difference model.
Oh, that'd be cool. Yeah. Oh, I'll talk to him about that. I did use a delay difference model for my PhD work, for my simulations, and that was worked quite well.
I did this for tunas back in I had an age structure. I looked at the age structure for the first ever. I think for tunas it was 5 years, but for sablefish we do the first 10 years.
Yeah.
And then everything else goes into the delay difference.
Hmm.
It's really fast, and the way we use it, because we're replacing the assessment model in the sablefish, which used to be just a simple
Right.
shape for production states-based model.
Yeah.
And because it's symmetric, it really underestimates biomass.
Yeah.
Grows too big. So we're first we unleashed this model on the data, and we're like, it's like, oh, it's freaking way off. It's terribly biased. And then I was thinking, like, well, why don't we give it all the recruitments? There's no reason why you can't give it all the information up to today.
Yep.
The operating model has.
Yep.
At least you have to give it once a day.
Yeah. Yeah.
So if you do that, it'll track really well. But the operating with reasonable error distributions.
Yeah.
So that's been going really well. And it's super fast.
Okay. Yeah, I'll talk to Sam about that. See if that would work.
Cannabis donation
To the halibut. Yeah, but I think I didn't want to do this without an estimation model, I think, because that's the whole.
Yeah, it's not really.
So that's still in progress for the SRB to consider carrying forward. Another recommendation the SRB made related to overfishing was the justify alternative timelines to the 3-year rebuilding period specified in the proposed definition. And what we looked at was the proposed definition from before, and we realized the proposed definition didn't make sense. So we have redefined overfishing, as seen here on the bottom, to be more consistent with the entire harvest strategy policy. So the overfishing definition, where the stock is subject to a level of fishing that will move it to an overfished state with a greater 50% probability within 3 years at a constant mortality measured biomass. That is if you're above overfishing. The latter part of the sentence of this definition is what has changed now. And that's when you're below overfished and you should be in a rebuilding plan. And that was where the SRB had concern, is we were specifying it should rebuild in 3 years. So now we've just said preventive rebuilding to a not overfished state within the required time frame and specifications of a rebuilding. So now it's internally consistent.
So this is really different than overfishing in the US definition, which is essentially just that great swine. And I know that is on purpose,
Yeah.
but this really, as you know, makes the overfishing definition conditional on current status. Current status is good. Then there's very little chance of overfishing. Raise it to the point where within 3 years you could drop it down.
Yeah, well, I mean, current status is 38, 36%. Yeah. Yeah, it's around there. And looking at the decision table, so we would be able to use the decision table to define overfishing. All of the harvest levels specified in the decision table last year, none of them would have been overfishing, because we're still above that overfished level by quite a bit. And overfished level is 20% relative spawning biomass. So, it would take quite a bit to get there. And so, but the idea that we had was, if the biomass is high and they did want to fish down a little bit, they had that flexibility, opportunity to increase the harvest rate to have higher TCYs or whatever it is, and not be declared overfishing when you're still at a good status.
On the other hand, the value of overfishing, an overfishing definition is partly to sort of notify you in all caps that the current rate of fishing cannot be continued.
It's not sustainable.
Yeah.
Yeah, and
And it doesn't fulfill that function
Right.
when it's essentially a, you know, break glass in case of emergency kind of thing.
certainly. Within, yeah, that is a good point. With an annual stock assessment, it's probably not a huge risk in my mind, because you are adjusting that fishing rate every year.
But this might never go off until you get to
Yeah.
a really low state, right? And
Yeah.
I think this definition of overfishing makes it where you schedule warning sign. That light's not gonna come on until you're in a pretty bad biomass state.
Mhm.
So it doesn't warn you that fishing mortality rates are too high for all. I'm sure the commission likes it because they can always say they're not overfishing.
Yeah, it offers that flexibility. Would it be worth bringing in the concept of, well, I mean, it would be pretty obvious, the reference level SPR. It would be obvious if they're exceeding or chose a quota or TCY that would exceed that reference level. So if they chose a TCY with a SPR 40% when a reference level is 43, that would be obvious
Yeah,
thing, but it wouldn't be a flag necessarily.
right. I mean, that's a pretty subtle way of talking about it.
Mhm.
Whereas if you called a certain SPR, well, SPR 40% or whatever you want to set the threshold at overfishing.
Yeah.
That's a lot clearer.
Yeah. So I see it as that there's two concepts of overfishing. One is a sustainable overfishing level over multiple years, and then overfishing level for one specific year. We're trying to capture that exact point. It's like, especially for a brand new fishery, you might fish the stock down quickly to sustainable levels and then manage it at a sustainable fishing level. But with an overfishing definition, as you were suggesting, MSY based or something, you would have to fish it down at a much slower rate to get to that point, which may not be a bad thing.
I mean, maybe that was relevant in 1910s. But
Yeah,
We're not in that world anymore, right?
Yeah.
Where they want to take advantage of the capital built up.
yeah,
And you're not trying to define fishing the rest of the world.
yeah, true.
So, I mean, I guess one of the practical implications of this would be about how the fishery is perceived externally. And having it by its own definitions be in a situation of overfishing is probably a bad thing for communication perception.
Right.
So there's that, and this definition has the benefit of essentially never resulting in overfishing.
Unless you're
But
a,
I think it's not very useful as a warning tool for managers.
Is there a flip side though? When you get really close to the threshold, you're very close. You could be, by this definition, you could be fishing. Where you might not flag that as being fishing in excess of MSY, depending on the demographics. You're right at 30.1%. That's why I was going with the theory.
That you just brought up that I had a hard time convincing.
of what the,
Just using FMSY is, that's, it applies everywhere at all times. And you could say, in a reporting sense, currently, fishing intensity is SPR 40%, which technically under the standard theoretical definition of overfishing would be fishing condition. You could say, yeah, but the stock is, 20% higher than B0. Fine. So, okay, go ahead. Just don't do it forever.
But you still have that red flag that many people would just say, well, you're overfishing. End of story.
Yeah, but that's the way the world is. Like, I mean, there's exceptions. Everybody's doing something slightly different at all times. Like, I mean, we use, in 2 cases now, we have harvest control rules that specifically fish at 1.2 times FMSY. It's stock is like one, so it works out 20% higher than BMSY. You can fish it 20% higher than FMSY, but the rule says you ramp it back down.
Right.
Whereas under Magnuson.
These are Canadian fishes.
We already consistently report the TCEY that corresponds to a fishing intensity that matches MSY or FMSY as the anchor on the right hand.
And
That's
that's,
already the column that sort of sets the management zone into the decision.
and that's the concept is that the FMSY or the SPR MSY is different than the reference SPR 43%. And so that is in my work plan after I recondition the operating model is to determine what the MSY SPR is. And that is typically around an SPR 30%.
35, I think.
Well, no, 30% was the last one, and then MEY was about 36%. Yeah, so the SPR MSY was 30%, and some initial things with the updates that we've had in the last 6 years ago, I did that analysis, with, it's showing that it could be more like 28% SPR. So that then it becomes is overfishing relative to our estimated MSY, which like depleted would have to be redone every so often, recalculated, or is it relative to the reference SPR? And if it's relative to an actual, our estimated SPR MSY, as Ian pointed out, it's bookended in the decision table where that rightmost column is the TCUI associated with it.
Hardly ever fishing.
Yeah.
Yeah. Whole thing is set up, you're considering those as targets, and you've got this buffer to recognize that I think that's what you're talking about, the reference being one you tried to hit, it's not actually the one. The stock system comes along and says, well, this is what you actually hit.
So overfishing.
So you're got that too, right? You've got those 2 buffers in there. So why not use the standard definition? Because you probably
The MSY.
you're never going to be declared overfishing unless you get down into these things, low states. Well, even then, I mean, if you're
The low states
your
or
SPR MSY is 28-30%.
and I'll say in hindsight, when the population was large due to large recruitments and large size of age, what were some of the highest SPR values in the early 2000s? They were in the 30%. They were around MSY at MSY.
Yeah, but only in retrospect,
Only in retrospect, right?
not at the time.
So
So
there could be the case where, the commissioners say we want a high quota, 8 million pounds or something, but we're taking advantage of this.
So for Marine Stewardship Council, they have a thing for RFMOs,
Right.
MSE to say that you're referring to this part of strategy or management procedure is achieving the intended exploitation rates.
Oh, really? Okay.
So what you're doing in going back and saying, okay, what did we actually achieve? Like that's relevant for MS. That's what C would want to see.
Yeah.
Even then, you're not. You may be overfishing in a super high biomass, like you're saying. Same thing happened in Atlantic. well above FMSY. Yeah.
I'm wondering for overfishing, if it's worth to bring both of these concepts in for the harvest strategy policy. To have, I mean, I like the idea of fishing at a short-term level that would take you to an overfished level. That, in my mind, is what I think of overfishing as. You want to avoid overfished. How do you fish such that you avoid that? But I see also your point in thinking of the long-term level, MSY or whatever that you want to define that as also a threshold. Could we have both of these in?
The other criteria I think of is avoiding redefining terms that are already fairly well
Yeah.
defined in fishery management.
I've heard Sean say
And overfishing is one where there does seem to be pretty wide. Overfished. Overfished is. I like where we ended up with overfished.
The only difference between the theoretical overfishing and this one is really the 3 years.
Yep.
Right?
Mhm.
Because it's that.
Yeah.
Because the MSY proxies are all the way on the right in this table, and there's something that they're already trying to avoid. It's, I think having overfishing be based on FMSY, like it is everywhere else, doesn't create the problem where the light's always flashing.
Mhm. And the fact that fishing at MSY for Pacific halibut doesn't meet the objectives, the other objectives of the fishery.
Well, that's what I was gonna say, like, how is this being used? Is it being used in MSE objectives? Because who cares, right? It's really about the performance, the other performance
Yeah.
metrics, not really what your specific SPR is at any given time. That doesn't. So this would be something that would be aspirational in a set of aspiration objectives, right? This kind of things.
We just stated in the harvest strategy policy.
Yeah. Which, is consistent with like even the way you set up your decision tables is already meeting that objective because you're not even truncating all your decision options.
Just
So what are we
interested.
looking for? What do you want?
Well, I think we're at two different definitions of overfishing, and where I'm at is really interested in what Ian said. Is like, is there a scenario when we could be fishing at FMSY or SPR for MSY or whatever, FMSY, that would actually lead to overfishing based on the definition on the board? And, is there a level of biomass that would be risky to fish at MSY, even though, and we want to flag that as well. But I think we'd be approaching overfished, approaching depleted, control rule would be coming in. Like getting to that would be a pretty rare instance.
And you've got, you don't want to have too much redundancy in the overfishing and overfished definitions as well, which is why.
So it's completely redundant here.
Yeah. It's not completely. It's close.
The theory is, that fishing at FMSY will bring you to BMSY. So it's kind of what this is saying.
Yep.
Because overfished is anything below BMSY.
Overfished is not anything below BMSY
In
here.
theory it is, but not here.
I mean, we've got around that with Axel a few times on that one.
Yeah.
Everywhere else it's fraction.
The idea behind the theory is that if you didn't fish, if you added some biomass, you would get more production.
Yeah.
That's the technical definition of overfished.
That's one.
Well, it's the mathematical definition. I don't know what other way you want, I mean, yeah, then there's variations that different jurisdictions use, but the mathematical definition is pretty straightforward. Everything is a choice.
So I think what I'm looking for, what we're looking for from the SRB here is the discussion that we've had. What's an SRB recommendation? Does the SRB recommend avoiding this sort of short-term definition and using a more long-term definition that incorporates long-term equilibrium sustainability into the definition of overfishing, using a more of a MSY-based approach?
That's my preference, but I don't know.
And that's something we can present to the commission and have a discussion about.
You know, like I would state it in terms of the overfishing, and I think that's what we're talking about here, is overfishing being tied to the FMSY or SPR, FMSY proxy, I guess. is what we're talking about. So just has to be tied to that.
Yeah.
Fishing
Which
at a
is-
greater level than the FMSY proxy.
Which is different than the reference SPR level
Right.
and still gives them the flexibility to depart from that reference. And I think that that's going to be a key statement for the commission to understand that, okay, we want the ability to maybe take a little more when times allow us to take a little more, take less when times need us to take a little less. Okay.
Overfished, I mean, you can call it what you
Okay, thanks for that discussion. That's really good, and we'll certainly relay that to the commissioners. So if it's all right to move on from this, the last, second to last topic is just an update on what is happening with the interim harvest strategy policy. So we've had 3 workshops with commissioners this year, and they've all been fantastic. I feel really fortunate to be able to work with the commissioners that close to this. And I think the commissioners, I have seen that the commissioners are very engaged, all of them in this process, and very interested in coming up with a harvest strategy policy for adoption. So with that being said, at the last workshop we had, the commission is indicating they want to consider this for adoption at the 101st interim meeting on 2nd of December this year. So we have a draft pretty much put together. We'll introduce the overfishing stuff that may come out of your recommendations. And that draft is actually an info document on the SRB website. Have a look at it if you haven't already. But they're actually, there's been some changes since the annual meeting this year based on these 3 workshops. And a lot of it has just been wordsmithing. So some of the noteworthy improvements, we've really clarified the language for the objectives, and we made it very succinct. Our thought and our discussions with the commissioners on the objectives was this is a pretty high level policy document. We didn't want to go into too much detail on this stuff. Keep it, where the detail would then come in other documents, aspects of the commission's responsibilities. And so I'll show you the definitions for the objectives shortly. We've introduced definitions for what are short-term and long-term in the harvest strategy policy. And that was based on some suggestions Sean had when he attended the 2nd workshop that we had with the commissioners. And so it was unclear. And so we defined that a little bit. So there's a paragraph in there now that provides a little bit of insight into how these are then used in the MSE process. And then we added in a description of depleted. So we brought in the description of depleted, but we haven't provided the threshold yet. But we had a long discussion with the commissioners at the last workshop, And they're all in agreement. I'm pretty sure they're in agreement that depleted concept is a useful concept to have in there. And we put a footnote in the harvest strategy policy that work continues to define a threshold and management action associated with a depleted level. So those are the big things. I just want to show you, one, these are the objectives, and we've actually worked not only with the commissioners, but with the MSAB on defining these objectives. And the MSAB was actually very good at making them more consistent in the language. So if you read 1 and 2, you'll see they're sort of phrased in the same way, so that they're pretty easy to understand. The third objective is the combination of what was 2 objectives previously. And there's no, this is one that's been a lot of discussion because it's simply maximizing short-term post-wide yield while minimizing annual changes in the mortality limit. That is a bit of a, I don't know what you call it, Sean, more aspirational, but it's not a clear measurable objective. And so we've talked to the commission, what does this mean? Shown them plots of the trade-offs. And Sean, you showed us a plot of the shrimp trade-offs. And then what I showed the commissions at the last workshop was actually that same plot, except for Pacific halibut. And it shows a U shape and a minimizing variability and what it needs to yield. They had a pretty good discussion about it. So again, these objectives are succinct. They may not be really detailed, but I think that's the work of other documents. And what another harvest strategy policy I'm familiar with is New Zealand. And what they've done is they have their harvest strategy policy document, and then they have a second document that's called the operational guidelines. And that's where they get into the details that the scientists would want to read. And so I'm been sort of thinking about, well, maybe we can do that. And the commissioners have already recommended creating a second document that explains the elements of a rebuilding plan. And there is one in Canada, and they sent me an example of that. That's separate, high level document. So related to these objectives, we've included this figure in the harvest strategy policy, which tries to indicate the hierarchical aspect of them. And really that these top objectives that are related to relative spawning biomass 1 and 2 are really objectives you want to meet for the sustainability and optimizing fishing activities before you start working on the third objective on the bottom of optimizing yield. So some other things that so these measurable objectives here are what was shown on the previous slide, but we've also stated a general objective such as provide stable fishing opportunities to really give it a high level aspect of that. And then green is showing sustainability conservation objectives, and blue and gray are showing the more fishing related objectives. Text is a little bit small.
I like this as I think you alluded to, this last number 3, the measurable objective is not exactly measurable because you can't optimize for both of those.
Yeah.
Trade-off.
Is it?
But you just have to word it differently. You'd have to pick the trade-off that maximizes the combination, versus variability.
You should put falls in the put it up on here.
Yeah. Yeah, we've had some discussion around that with commissioners. It just has like
There's agreement on how to weight those two on
Yeah.
trade-off. That's why they want to choose, because their discussions are around, well, is it worth it to gain 1 million pounds of yield long-term to reduce variability by 2%? Does it take 4% to be worth it? That's where we can't solve it for them. They have to make that decision.
Yeah, so we do like a whole bunch of scenarios, like we solve that optimization and weighting combinations of the two variables, and then also report what the third one comes out to be, because we use 3.
Okay.
But you can only do the optimization on 2, and then you see, okay, what does this apply to the third? And it's the, the limit reference point probability. And we thought we were gonna be doing like 10-year average yield, but they wanted to replace that with the variability. Variability is their primary concern.
Yeah.
Which,
And we found for some user groups in Pacific halibut fisheries, variabilities is more important than actual yield for them.
yeah,
But for
until
other user groups, yield is more important than variability.
you
until-
show them
yeah,
like, oh, you want to
exactly.
minimize variability? This is where you can do that.
Yeah.
Keep it low every
You
year.
have.
Yeah. Yeah, and so I think it's challenging for us because the commissioners and the stakeholders, especially those involved in MSAP, are still learning what their priorities are.
Sure.
I think over time, we may get a better idea of how to exactly maximize or optimize this trade-off.
It's funny.
I don't have a problem with it. I just,
Yeah.
noting that there's a solution to.
Yeah.
I'm
Yeah.
sure you've had a lot of discussion.
Yeah, we've had a lot of experience with that.
It's measurable. It's just not solvable.
Yeah, there you go.
We had our shrimp meeting a couple of weeks ago. They're like, okay, Sean, take it away. And I was like, well, I'm going to tell you about my breakfast. Because I was sitting in the hotel having my breakfast. I'm the only one in the restaurant. And some server is bringing this guy over. And I could hear her saying, like, is anywhere particular you want to sit? I was like, no, I don't care. And as they're coming towards me, she's like, okay, how about here? Oh, no, I don't want to sit there. It's too light. And then they turn, start walking the other way. And she's like, well, how about over there? No, it's too dark over there. And then he's finally like, how about over there next to the window? And I was like, as this is happening, I'm like, this is perfect. I'm going to start the meeting this way. Because it reinforces that like nobody knows what they want until you show them some options.
Yeah.
All right.
And that is so true how this process has gone.
You say, I'll tell you what I think you should do, and you'll tell me why I think,
Yeah,
why
no,
you
no,
think I'm wrong.
Yeah. I'll tell you what to do and you'll tell me why I'm wrong. And that's actually worked great with some of the groups that I've worked with here. Okay, so those are the objectives. And then I mentioned we've added language on depleted into the harvest strategy policy with a footnote that this is ongoing research. So the black is text that's been there describing overfished. The red is text that is now describing depleted. And we've worked with the commission and they've made a couple of changes to original language on this, which I think is good. So they've been involved with this and we've had lots of discussion on it. I'll just let you read that for a brief moment. Yeah, if you have any suggestions. Here.
That last sentence, there's a lot of leeway.
And the last sentence is there as a bit of a placeholder as well to indicate that we haven't what those actions would be. And the footnote states that those actions could be determined in the future, or specifically as part of the management procedure.
So in general, I think, definitions of limit reference points. But in this case, I would take like a sentence that says this measures the effect of only fishing rather than the effect. That sentence, I would move to the top because that's what it is. So, the overfish limiting reference point is a measure that measures, and then that sentence, right? Measures only the effect of fishing. And then you follow up with, how does it do it? Because this one, it's like, somebody's trying to find out like, what is it? What is it? What is it? And you're telling them like how you do it, bringing in other concepts of relative spawning, like it's getting complicated versus a very simple statement, of what it's trying, what it is.
Yeah.
And then you can give as much detail as you want.
Maybe switch to second.
Yeah.
That second sentence on the top.
The second sentence in the black. There.
Yeah, dynamic calculation.
I know.
pertains to relative spawning biomass being the estimated value relative to the estimated spawning.
Jeez, when you read it out loud. Okay, yeah, that's good feedback.
And then I think the red, you almost want to create, you want to now say, now define depleted. That's a
Depleted
new
is,
concept,
yeah.
right?
So have it, the overfish limit is blah, blah, blah. Depleted is,
And then the same idea, you might want to take in the why these are different after you said. It's-
yeah.
So it's different from fish because natural variability.
Okay. I'll work on that and I may run that by you tomorrow. Thanks for that. But I think what I'm really proud, excited about is that we have this concept in the harvest strategy, these two concepts. And the commission is really feeling that they've really adopted.
It's two concepts, overfishing and overfish / depleted, or just the overfish.
The overfished and depleted, and bringing in the depleted concept,
Yeah.
explaining those two. That's what I'm feeling is good.
But
And I'll-
overfishing is not in there yet.
It is.
It is.
Yeah, that definition that was there, and then based on your recommendation, we can present to the commission alternative definition for overfishing. But yeah, so there's 3 limit reference points in there, the overfished, overfishing, and depleted. So what does this process look like? Well, one, we're going to, we're scheduling an MSAP informational session for them to have a look at this harvest strategy policy in October. I believe that's October 22nd. And that'll be a virtual discussion with the MSAP. Bring it up at the 101st interim meeting. And hopefully for adoption at that point, because if it is adopted, that'll really help with the stock assessment in identifying how they built the decision table, basically, make sure it's all clear. Once adopted, it will then just be published to the IPHC website. And then, as I mentioned, we'll work on some supplementary documentation to make sure that a lot of the operational stuff is really clear. Yes. So we're looking forward to the remainder of this year. And, you know, I just want to say, this is a lot of work. A lot of people have gone into this, especially the SRB, and really appreciate all the input we've gotten from the SRB over time. The MSAP over time has put in a ton of work on this, but the commissioners, especially recently, have been putting in a lot of work on this as well. It's certainly due for IPHC. Especially with the new MSC guidelines. I don't even know if I haven't been paying attention to those, but all our FMOs are supposed to have a harvest strategy policy or something like that now.
Yeah.
I don't know if I heard they put that out, that standard for something, but then they backed off and they weren't holding them to those standards, but I'm not sure where that's at now. So, but it's something that we really have to get done here.
Yeah, so the challenge is going to be well-defined, pre-agreed harvest control rule
Yeah.
that has been demonstrated and then achieves.
So,
Decision table is not consistent.
yeah,
Go
exactly.
back and try to show, okay, well, it is in practice, the realized behavior, it does do this, but I don't think that's.
Yeah.
Applies.
Yeah, those discussions will be interesting. It's part of the reason we did a lot of work on introducing decision variability into the simulations. So cross that bridge when we get to it. And I guess another noteworthy change to the harvest strategy or addition was there's a table with a schedule, example 3-year schedule, and what that looks like in determining exceptional circumstances, the stock assessment, but also the commission asked, when we adopt this harvest strategy policy, is that it? It's like, no, they're in the schedule. There's occasional points where it can be updated when necessary. And the commission was like, well, we don't want to update this often. So,
You hear them say
yeah,
that?
they came back to me with that. And so we've put it in there. It's like the harvest strategy policy may be updated when necessary. And I can't remember the exact language, but more on a 3-year process that corresponds with the reconditioning of the operating model and new simulation analysis, eventually. So linking it more to the work that would go on to improve the harvest strategy policy.
That's good, but I mean, even a 3-year timeline for doing that seems pretty frequent for a strategy policy. Be hard to have any information about how it's working.
Yeah.
You've only applied it for 3 years.
Yeah, that's for sure. But I think if it was adopted this year, that there might be some additions in the next year or two, just based on the work that's being done, completed work. We'll see where we get with open vision. I just swap it out for a new definition. But we're looking forward to adoption.
Yeah, great.
And then, so finally, the MSc program of work for 2026. What are some things we're thinking of doing? One, reconditioning the operating model after the full assessment. Of course, comparing previous results to these new updated results, see if it's consistent or not. Work with the SRB and the commission to define this depleted threshold and management response. Do the simulations to detect overfishing. See if we can. And examine productivity scenarios to better understand the current conditions. That's looking at what is MSY. Or I guess, no, this is productivity scenarios that I showed you last time. High, low weighted age, high, low recruitment. But yeah, I don't have on here to look at MSY. What that is with the updated operating model. Something I just realized is if we are changing the definition over fishing, I'm going to jump back real quick.
So you're gonna create a fork, you're gonna kind of fork the operating model. Current one is gonna be is what it is as of today, whatever day you decide, then you're gonna start a new branch. Because it would be nice to be able to go back to the
Yep.
operating model and run projections and say, okay, this is what we thought was going to happen then.
So yeah, every time, I think for every major meeting, like an MSAB or an SRB meeting, I have all this in GitHub and I create a release. And so I can just download that release and rerun everything. The other thing I've done is actually I have some virtual computers and I leave one virtual computer set up with an old operating model. And I can just turn that on and then run it. So I have a couple of paths that I can do. So I believe let's back up one. The recommended secretary evaluate assimilation to the ability to detect overfishing based on the proposed definition. The proposed definition is this definition. So if we do change the definition of overfishing, that's going to make that recommendation. So that's something that I'll just be aware of. If the definition is just exceeding MS1, I suppose I could still do some simulations, but
Yeah, it's not really simulations of that.
Yeah,
It's
yeah.
just taking the distribution of uncertainty,
yeah.
seeing where you are in it.
So it's something to be aware of. If this recommendations pass forward, I'm still going to work on a more realistic estimation model. But if this recommendation is passed forward, if we do change the definition of overfishing, it might be a good recommendation.
Can we recall a recommendation?
Can.
I suggest we recall that one.
Yep, I think so.
We'll recall it's a different.
Not like a recall in your car, like a remembrance. Recollect.
Is that what it's called? Recalling?
Yeah, recall this recommendation.
Full recommendation.
Although we've said that before in a different, meant in a different way. Retract.
You can retract it if
We
you
want to
want.
retract,
Yeah.
right? Is that what we want?
I guess so. That sounds like it's.
No, it's no longer relevant.
It's the life. Definitely.
All right, well, that was a bit of time, and I certainly appreciate your attention this morning. I don't have any specific recommendations. You're all really good at creating those. But if there's anything else you feel should be added to the MSE program of work or the harvest strategy policy, I'd love to hear about it. But this was a really, really good conversation, and I certainly appreciate it.
It's really your work.
Yeah, it's
presented
great.
so far. Yeah, it's been great.
And seeing the MSC work come
Oh my
so
God.
close to
Getting there.
adoption.
It's so cool. It's so cool. I've been telling the MSAB, it's like, this is your product right here. You know, you should be very proud of it.
So what does it, what are the implications of adopting the harvest strategy policy? Does that mean the management procedure is in there as well?
Yeah.
Or-
Yeah, right now, there's the reference SPR 43% in there based on some previous work, but we had the discussion with the commission. If during adoption, if they did want to change that reference SPR, because the MSAB made a recommendation to change it to 46% based on this curve of variability and yield. It's sort of the bottom of the curve is 46%, but the difference between 46 and 43 is small. So the commission may have that discussion on changing that during adoption. But yeah, it would contain that management procedure, but also contains the language of potentially deviating from that reference level, but that's their anchor point really in the decision table. And so it's basically a high level policy document explaining the goals, the objectives, the default management procedure is what we call it. The process of the assessment, the schedule of events, the presentation of the decision table, how commissioners make decisions, and then how the harvest strategy policy was evaluated a little bit on the MSC process.
So for MSC, you should probably have a column in the decision table that says, it clearly labels that as your pre-agreed harvest control goal.
Yep.
Right? And then
That's in there.
that way you can say, yep, we have one, it's right there, anchors this. And then how does it shown to meet exploitation rates and stuff? Is like,
Yeah.
yeah, we include the variability in the simulations. It's all good.
Yeah, so we have that. That's usually the center.
It's the reference.
It's the reference label in the center.
It
and-
may not be in the center if the commission,
Yeah,
like last year, the commission wanted to see more options below the reference. So it wasn't actually in the center, but it was still there, prominent. It was
Bolded or
below,
something.
it's MSY, MEY, whatever options they want around the reference. And then some really low values so they can see what stock dynamics are doing if they're fishing.
and then the
Basically-
surplus production fits in there.
Certainly to our discussion last night about anchoring. This is
Yeah.
essentially what you want us to do, right?
Right, it is.
Right.
Discussion.
The commission has typically been anchored on that reference level, but they also anchor themselves on the past TCY, the TCY from the previous year as well. All right, well, thank you very much. Probably brings us to a break.
Break time. So break and return at 11.
Good morning. For those online, I'm Ray Webster. I'll be presenting on the FIS designs for the coming 3 years and particularly focused on 2026 design, along with some updates regarding the space-time modeling. Pretty much most of the first half of this is the same material that was presented in June. The introductory slides, so I'll try to go through those quickly. Most people have already seen this many times. FIS is our most important source of data on Pacific halibut. We use it for estimating stock trends and distribution. Provides an input in the stock assessment, as Ian has talked about already in this meeting. Provides biological data for the stock assessment. We've had an annual FIS undertaken since 1993. The design was expanded in that first decade and to include sampling in all regulatory areas, and further expanded more recently since 2011 to fill in gaps in the FIS that were there in the previous design. The full FIS grid looks like that with the orange dots, 1,890 stations on a 10 by 10 nautical mile grid in depths of 10 to 400 fathoms, 18 to 732 meters. And the data that we get on the FIS is augmented by calibrated data from the NOAA Troll Survey and Alaska Department of Fish and Game troll stations in Northern Sound. So as we're not able to sample the extensive region, a low density region of the Bering Sea very often. And nor can we sample the full FIS grid each year. It's logistically challenging, cost prohibitive. So we prioritize our sampling effort based on scientific needs, try to get precise estimate of indices and of abundance and distribution with low potential for bias, which may require more frequent sampling in areas with high variability, for example. Our second priority being cost effectiveness, which was reworded this year by the commissioners. Used to be long-term revenue neutrality, balancing operational feasibility and logistics, cost, revenue, and scientific needs. Summarizing those in tabular form, we also have a tertiary objective, basically minimizing our removals, assisting others in data collection, such as other agencies, on a cost recovery basis, and addressing specific commission informational needs. This is the timeline of the review process. We are here at the SRB review, the second SRB review. The data for 2025 will be finalized in coming weeks from the FIS, and we'll be then modeling those data. And that will feed into the review process for designs for next year. Okay, more recent history. In 2020, following the expansion, we rationalized FIS designs, recognizing we couldn't sample everything every year. We did a random sample in the core areas 2B, 2C, 3A, and 3B. We don't need to sample every single station within that those areas every year, so we picked a sample rate that maintained similar survey effort overall to previous years. We sampled blocks of stations elsewhere because densities were much lower. It was not efficient to sample in a randomized fashion from those other areas, but we prioritized the sampling to maintain precise estimates with low bias. Unfortunately, that year, COVID-19 hit and the FIS was reduced to just the core areas. In 2021 to 2022, the proposed design was largely implemented with that random sampling in the core of the stock and blocks of stations elsewhere. Although Western 4B was not sampled in 2022 due to a lack of viable beds in that region, hasn't been sampled at all since 2019. Reduced designs were implemented the last 3 years with little sampling outside the core areas in 2023 and no sampling in 4A, 4B, or 4CDE that year. Further reductions in 3A and 3B in 2024, some sampling in 4CDE. 2025, sampling in 3A and 3B was chosen to complement that, the previous 2 years sampling in areas we hadn't necessarily fished the previous 2 years. And we sampled higher density parts of 2A and 4A, 4B for the first time since 2022. Summarizing, not including 2025, which at the time that this was made was still being undertaken, but the most recent sampling year by station up until 2024, showing that parts of Western 3A, Western 3A, Eastern 3B, and 2C, 2B, and parts of the Bering Sea have been fished most recently. Most of the stock has been fished in the last 2 to 3 years, but there are parts of the stock, and particularly 4A, 4B, and 2A, that haven't been fished since 2020 or earlier. The 2025 design is implemented, it's planned to be implemented, look like this. The FIS was successful in fishing these stations for the most part. We had some modifications to the design in Eastern 4B, where conditions on the water made it unfeasible to fish the easternmost stations, and they were replaced by other stations to the west of the block of stations in this map. And 6 stations were moved in 4A for the same reason. So this design, while relatively sparse compared to historical designs, does include sampling in all IPHC regulatory areas except for CDE, which is covered by the NIMS Troll Survey. So we do have data from all the regulatory areas, even though there's substantial gaps in the design. So as noted, until recently, the designs targeted a random selection of stations in the core of the stock. Chose that method in 2019 over proposal to instead fish selection of charter regions. We came full circle, and 2023, the Commission directed us to evaluate block designs, mainly motivated by reducing cost. These designs can be more efficient. Stations are nearer to each other, fewer gaps, and resulting in potentially longer running times. And so that's been the focus of our designs since then. So we developed what we called the base block design, which was evaluated for the Commission's consideration. 2024 prioritized some manual sampling in each biological region for stock assessment purposes, ensures all charter regions in the core of the stock are sampled over a 3-year period. Coverage in other areas is prioritized to minimize bias potential and maintain CVs below 25% for indices of density and abundance, noting that our previous target range was below 15%. So some relaxation of that outside the core of the stock. The sample blocks, just charter regions, will be rotated over time. So this base block design, again, I presented this in June, for 2026 to 2028, shows that rotating nature of the design. For example, in 3A, we sample 4 charter regions, 1 out here, CC boundary, and 3 over here. And then we switch to the other 4 charter regions. So we have complete in 2027. So we have complete coverage of 3A over a 2-year period. For 3B, which is an uneven number of regions, we fish 2 each year and have complete coverage over a 3-year period. And likewise, we're prioritizing sampling areas like 4A, 4B, and 2A to ensure that we're covering all of the stock over a relatively short period of time, but with more frequent sampling in areas with higher density, greater variability. In this case, that would be Eastern 4B, Western 4A, and higher density parts of 2A. Noting that, as we talked about yesterday, 2A may be high priority for people who fish in 2A. For information about local management, but it's a relatively low priority for the overall purposes of the assessment or understanding coastwide stock trends or regional stock trends, given the low densities, low proportion of biomass in 2A. So we don't have sampling in 2A proposed for 2026. Sampling.
So 3B,
3B.
you said over 3 years you get
Yes.
complete coverage, but it doesn't look like you ever touched the Western 3B.
That's a good point.
It's okay.
We did it this year, and so I'm gonna. That's a good, but that isn't part of the 3 years. You're right.
And when's the last time Southern 2A has been sent?
California, 2017. Yeah, that looks like an error. Sean, thank you for pointing that out. After all the times I presented this, notice that, including me, I think I've likely just. I think the final map should include. Right, it should not have been those central regions. It should have included western part of 3B. I'll fix that for the interview.
26 and 27.
20, yeah, there's going to be some overlap. So we're trying to, I get a feeling that, yeah, anyway, I'll look at that. There is a version of this which is right, and I didn't put the right one up here. Everything else looks okay, I think. And the coefficients of variation from those designs would maintain very precise estimates in the core of the stock, CVs below 15% or below. But as I mentioned, below 25% outside of the core of the stock by regulatory area, more precise by biological region and coastwide. Oops. So the focus here is on the 2026 design. These 2027, 28 designs are nice to see where we're going, what we plan in future years, how they're going to complement the designs we're proposing for 2026, but they're likely to change given what we actually fish in 2026. And so the base block design for 2026 is highlighted here. The key features are outside of the core of the stock is that we have no sampling on the Bering Sea shelf edge. We have the sampling from the Troll Survey. We sampled part of this in 2024. So it's not a high priority given limited resources for fish sampling. Eastern 4B remains the highest priority part of 4B. We have 30 stations out of 70 something fished in 2025. It would be desirable to get more complete coverage in 2026. So we also recognize that the same issues with tides and weather may affect sampling in the far east of 4B. 4A, we're targeting the southeast of the region, which hasn't been sampled since 2019. We had much higher catch rates than expected on the stations we did fish in 4A in 2025. And so there's been some indication that catch rates may have gone up in the commercial sector in this part of 4A as well. So that's an area that we don't fish in 2026. That'll be 7 years of not fishing. And not prioritizing 2A in 2026. So I've already verbally summarized that. This design is projected to maintain precise estimates, and by rotating the sample blocks, there's a low risk of bias in trends and stock distribution estimates. But it's preliminarily projected to result in a substantial operating loss for the FIS and require supplementary funding. So we developed alternative designs to in particular a design which brought the operating loss closer to $500,000, which is something that has the potential to be covered by a mix of supplementary funding and general funds from the IPHC budget. And this design includes projected revenue positive, one additional revenue positive charter region that's not part of the base block design in 2B that would help offset the costs of other regions. 3 other charter regions in 2B, 2C, and 3A, which have reduced coverage, 30%, 30 stations sampled per region to help reduce losses there. And 3 subsampled charter, and those are prioritized as they were among the regions not sampled in the most recent 1 to 2 years. But overall, it's not a very healthy looking design. Very limited sampling outside of 2C and 2B. And we note that these subsampled regions, this map shows a random selection of stations, which is not what commissioners want for operational efficiency. But yeah, but that's just an illustrative purposes and a priority. If we did go this path, priorities might dictate a different version of the design. So limited spatial coverage would lead to increased risk of bias, greater risk that stock changes would be unobserved. Space time model estimates for ensembled regions would drift towards the long-term mean in the absence of data. We'd have increased uncertainty in the estimates of density indices. The assessment model would rely more heavily on the commercial CPUE index as it did the last couple of years. It's unclear if the assessment model would be able to detect a major change in year class abundance. Current spatial variability uncertainty and this current magnitude of younger year classes, limited biological information, biological region 3 and stock's core. Projected costs are based on the assumption of a decline of 15% in price, recognizing that we had something in the order of a 30% increase in price in 2025. So we're being pessimistic, but not as pessimistic as we could be. And 5% decline in the stock, which is a pretty reasonable assumption. We had quite a bit of discussion with the commissioners about our level of pessimism on price, and they thought we were likely being too pessimistic with a 15% decline. They want to see costings for smaller declines, possibly as low as a 0% decline in price. We did look at before the work meeting a couple of weeks ago what an effect a 5% going to a 5% decline in price or a 10% decline in price would have. It's not as big as you might expect. We've reduced costs, I think, in the order of 5% is decline of something like $80,000 for the base block design and half that for the reduced loss design. I have to check that to verify that. But those are still preliminary costs. We're getting close to finalizing the costs for 2025, and that's going to could have a significant impact. Just a small variation in prices or in bait costs, and suddenly areas that aren't profitable tip over to profitability and can be used to offset the costs in other regions. Going to a 5% decline in price versus 15% brings one other area into profitability, which is in Southeast Alaska, and that can then be brought in as another area that can be fished to help offset the losses elsewhere. So those things, it's not clear until we get the updated costs, the finalized costs, how that's all going to play out. But in the meantime, this is the breakdown. The base block design projected to lose close to $2 million with 15% decline in price. And the reduced loss design, $500,000 as it was designed to do. So he also looked at several intermediate designs to give commissioners options to see what their priorities indicated they would like to spend money here or there, and then they could see how much each element of the design between the other two designs would cost. So tabulating those. So here's the reduced loss design here, projected to lose $537,000, assuming a 15% price reduction from 2025. We can then augment that design until we get to the base block design. So the first step is making the partial regions whole, and that would add a cost of $54,000 given the price assumptions. And benefit of that is having fully sampled regions instead of the random sampling may make it more attractive to bidders than sampling some 30 stations far from anywhere else, like in 3A is planned. And then 4B is the next priority because we want sampling in each biological region. And this would add that sampling for a cost of $265,000. And then adding something in 3B to provide greater spatial coverage in region 3 $163,000. 4A, which again hasn't been sampled, that part since 2019, $233,000, and so on. The final step is actually removing a region, the profitable St. James region, from 2B, and that gets us to the base block design. So since we last met, commissioners have secured a voluntary contribution from the United States of $513,000 specifically to fund the 4B survey, $265,000 for that, to fund the charter region in 3B of $163,000, and to partially fund the survey in 4A, $85,000 towards the $233,000 cost of that survey. So assuming that we would also, it's also desirable to fully fish those partial regions in 2B and 3A, and that a partially funded survey in 4A would not be viable to attract bidders, having 1/3 of the state of the footprints potentially sampled. And so we would prioritize finding additional funds for completing the sampling in 4A. We presented the commissioners with this design, which was one of the preliminary intermediate options, option 5, which includes the 4B sampling covered by a voluntary contribution, the 3B charter region, and fully funded versions of 4A and the partially sampled regions of 2B and 3A. That would have, based on current prices, again, emphasizing that assumption because there was such a point of discussion with the commissioners, and it's likely to be reviewed in subsequent presentations. That would result in a projected loss of $739,000. That includes the voluntary contributions. So that would still require additional funding for 4A of $148,000 and $54,000 to ensure the partial regions are fully covered. But this is still a substantial improvement over the reduced loss design. The spatial coverage of the FIS is much greater. We have sampling now in all biological regions and from 2B all the way out to 4B. There's a lot of gaps, but we do have a greater spatial footprint than we would have without the voluntary contributions. So if adopted option 5 would include FIS sampling in all biological regions, some sampling in all areas except 4CDE and 2A, noting that 4CD will be covered in large part by the neutral survey. It differs from the base block design in that it has 3 fewer charter regions than in IPHC regulatory area 3A, so 1/4 of the footprint, base block design, 1 fewer charter region than 3B, and has 1 additional revenue positive charter region in regulatory area 2B. While the reduced spatial coverage in biological region 3 relative to the base block design increases the chance of bias for that region, option 5 represents a substantial improvement over the reduced loss design in terms of both bias and precision. Will result in more representative biological data, more precise indices of abundance and stock distribution, and an assessment model that is less reliant on commercial data. And we note that there's still some information remaining to be finalized following completion of the 2025 FIS, including the final catch rates for all regions, average sales price of Pacific halibut, and final realized costs. And those are going to feed into our spreadsheets for projecting the costs for 2026, and they're likely to be revised, hopefully in a more optimistic manner. And we will also be, again, reevaluating those costs following the commissioner's recommendation to look at more optimistic pricing for 2026. So there are also decisions remaining to, and sampling priorities for 27 and 28 may be also revised based on the results of the modeling, stock trends, and so on. And there are decisions to be made regarding internal funding, including how to cover the additional loss of those other areas, possibly using general funds or applying the 2025 FIS surplus. So we're asking you to note this paper, but specifically, you already have a comment from Anne Marie on what commissioners might be interested in. That it probably would be helpful to the commissioners for you to weigh in on the benefits of the given that we're unlikely to be able to fish the base block design again in 2026, the benefits of going to option 5 in particular, given that there's some still uncertainty in funding elements of that design, and that the benefits of that relative to the use loss design. That would be useful to the commissioners to have their scientific input. This is kind of a self-contained part of the presentation, so it may be a good idea to discuss this part here, and the other part is less important, although potentially interesting because it's novel. But yeah, so there's some discussion on the first design. It's a good place.
Great, I think we saw the CVs for the base block design, but not option 5.
No, because there's simply not time to do that prior to the meetings, and given uncertainty in what and that's base block. Yeah, so where are we? Yeah, so the commissioners also noted that they would like to see that is something I could integrate into the once the data are finalized, which is coming up very soon, 2025, if we have a better understanding of what those CVs are going to be. So those CVs were projected based on a design that's close to what we realized in 2025, but with projected data from past years to 2021. So that's something that's been added. It's coming up. Present that to the commissioners. So I think that would be useful. They basically wants to see that.
Yeah, I think that'd be really useful for comparing.
Yeah. A challenge that we have is that when we're doing, if we were to do the base block design for a series of years, I think it would make a lot of sense to focus on the CVs because we would be covering every area for a reasonable interval. As we get to these very sparse designs, our concern is less the CV and more the bias, because we've got a gap. We haven't sampled an area and we might go 5 years without sampling. So things could change a lot. And so that's one of the challenges we've had with describing the costs of getting to these really sparse designs to the commissioners. Historically, we focused on the CV, but that breaks down to get these really sparse designs. My concern really isn't the CV. CV goes up, but it doesn't go up as much as our concern about bias goes up.
We were looking at 1 year ahead, and that's been the harder part to communicate because we quantify the CV and they can digest that really easily. But then bias is much harder. We've had a go of it based on how, and I presented something last year on that, and we try to do it again. I looked at the range of variability in the index from 1 year to the next. How much does it change in 1 year? By region, how much or area? How much changed in 3 years? And so we can look at then what's the potential for change over this time frame. If we're not sampling these regions and the biggest change happens, how might that play into the estimates at a regional level or coastal? So it's sort of a pretty back of the envelope kind of calculation, but it gave a broad view of the potential for bias. And it's quite, with the design we looked at, we fished in 2025, potential for bias was quite large.
And recall that we did the simulations to show that bias will actually translate through the assessment as manageable.
Yeah.
So it's a legitimate concern.
It is, yeah. So I'll do that exercise again for the commissioners based on what they for the interim meeting, but it's absolutely bias. This is the bigger concern right now.
Especially where we're in those decision tables and you're looking at fairly small probabilities and all this stuff. And it's like, well, it'd be worse than that. the less you sample, at least that's what you know, right? It's probably not any better.
I think there was a focus of the discussion last time, so last time or last year, that there were management costs. There were costs to getting the decisions wrong because the information feeding into it
Oh, yeah.
is wrong. And we noted that to commissioners, I think. Those things.
So if the total landed value of the TCUY is 100 million. Yeah. So it's 1%, 1.5% deficit. Can you, it's probably a bigger decision in this group, but can you allocate part of the TCUY to survey costs? So for example, I guess your vessels bid, what they're gonna charge you to do it, to do an area. Can you like pay them in quota? Commercial quota instead of cash? That way you can pull from the TCUY and just pay them in fish rather than paying them in cash. It's not for you guys. But that's what, in the sailfish, that's how we fund that survey, is like this research allocation that comes off the quota.
So the research set aside program.
Here it's like you gotta pay cash for stuff, which,
But the cash comes from the sale of the fish, so it's
well, that's
really the same.
that's paying, as of now, it's paying for all the other costs. So it's, you're partially funding the survey by fish, but fish clearly can't fund it all. At the moment.
The cost.
Yeah, but what's the reason why it's not doing it now? You've got, prices are different, costs are up, like those things aren't gonna change. Abundance is low, like those things are gonna be persistent for a while. So maybe it's something where, we've talked about this before, about the implications of smaller and smaller survey coverage when the stock is in the critical moments. You actually have worse information, whereas maybe that's a situation where you start pulling from the TCUY to fund the survey if you can. On a cash basis.
Yeah, I know we've talked about this before, but I always wish we had some kind of value of information calculations here. Understanding how tricky that is to do. Where we could trade off things like having better information at high abundance versus at low abundance. But to say like, what does this design translate into in terms of our ability to set a TCUY that achieves the same risk objectives, but gives us a bit more, given what better than
We translated last year, we took it all the way through
Yeah, remember
to,
that.
based on the bias, to say, if you were to reduce the TCEY enough to cover the potential bias that might be created by a smaller design, how much would that cost you? And it was several times the value or the cost of the survey itself. Presented that information to commissioners. The problem is to do the full simulation all the way through those quantities on every design. This is already the second or third iteration of designs we've been through this year, and this isn't the final one. We'll have to do another one. And so it's really not, given the timeline, it's not feasible to do those kinds of analyses, except periodically to remind them that
Yep.
to maintain the same risk level, I think the cost was like $5 to $7 million in terms of the TCUI reduction. And Alan showed similarly in the MSE, there's both a short-term in the assessment cost and a one-year decision table, but there's also a long-term cost that you can see in terms of foregone yield of reduced surveys. So we showed them that does more than offset the cost of the survey itself, but that still doesn't create the dollars on the table. That's right.
One thing we've talked about in the past with the different survey designs too is the ability to get all the necessary samples for the biological research. Is that worth discussing here, or do all these designs essentially are they equivalent in terms of the ability to get samples?
The same issues apply as we get to sparse disease. We have the potential for bias in biological data as well as the index. Because we're sampling smaller and smaller pieces. So if there's a new year class coming in and it happens to be distributed in the purple gaps that we're not sampling in the first year, or we have a small year class coming in and happens to be in the areas we're sampling and we overestimate it. There's
Yeah, I guess I'm thinking more about like the fecundity study. Are you looking at one of
yeah.
these designs? And say, "Oh my God, this is gonna destroy my ability to estimate fecundity," or?
I think it potentially will take longer to get what we need. This year, we started collecting fecundity 2 years ago, so 2023. This year was the first time we had been back to 4B since 2021. Yeah,
Yeah.
2021. So we actually got fecundity samples for the first time in 4B this year. So now we have sampling across all 4 biological regions now for fecundity. But if these designs keep getting sparser, that means limited opportunity to get those samples. And it just means that it could take a longer timeline to get what we actually need to look at like temporal trends and those kinds of things.
Yeah, yeah, less ability to look at temporal
Yeah,
trends.
exactly.
You know, you they sample the same
Yeah.
regions.
It was a positive change this year. Ray noted it early on. Our secondary objective used to be long-term revenue neutrality. It's changed to cost, recognizing that we're probably not going to be at revenue neutral all the time. So that was a positive step.
So in the past, we've endorsed surveys. I'm sure we can do that.
I don't think you need to.
Some kind of encouragement to move to a more spot providing.
Yeah.
I mean, I said, we need to say, financial side is really pushing us.
You could endorse the approach, trying to squeeze the most out of the resources that we have available.
Can we recall the cost benefit analysis that we did last year? And that conclusion about paying for itself several times over in opportunity cost? You get a chance to give us the document.
Okay, thank you. Any other input on that or?
Okay, I'll move on then. So modeling updates, this is focused on coast-wide modeling. It's not an update to the production version of the model that's going to be implemented this year for this data, but it's got potential for subsequent modeling. So this is I mean, even though I mentioned it in June, it's still fairly preliminary. There's a bunch of model checking and so on to do. But my purpose here is not to provide exhaustive details, but to give you an outline of the process of working through coast-wide models with an application to the histological data set. It's a nice compact data set with models that are relatively easy to fit. So presently, the IPHC model, we model Pacific halibut survey data by fitting a spatiotemporal model to data from each individual IPHC regulatory area. So essentially fitting 8 models. We have 3, one for each regulatory area, but we have 3 variables. 32 weight per unit effort, all sizes, weight, and numbers per unit effort. So I'm fitting 24 models each year. Each model runs in a reasonable amount of time, but overall it requires a lot of attention and a lot of intervention to get these things started and then processed. But then the model output for these regions is aggregated to produce estimates for larger geographical units, biological regions, or coastwide. And there are some advantages to this approach. Smaller modeling regions allow us to refine our meshes. We'll talk about what that is in a minute. Without leading to prohibitively long runtimes for the models. Faster model runtimes occur due to both smaller data sets and smaller modeling regions than if we were to try to model coastwide data as a whole. And it easily allows model parameters to vary spatially, having them estimated separately for each regulatory area. The drawbacks of splitting modeling, and you can probably think of other ones, but we have potential discontinuities at area boundaries due to differences in model parameter values between adjacent areas, because the parameters are estimated across an entire area. So when you try to mesh the 2 adjacent areas together, you might have, if you look at a map, you might see some discontinuities because the overall model is saying this should be a little higher here on this side of the boundary than that side of the boundary because we're getting a different one. Samples are drawn from posterior predictive distributions, which we use to create a time series of variables of interest, will not be spatially correlated across boundaries because we're fitting each model independently in each IPHC regulatory. So some of that spatial correlation is lost from across the boundaries. But in recent years, there have been substantial improvements in the runtime of these models. And I noticed it each year. I download the latest version of the software code I'm using, the R package RNLA, and my hardware gets better every couple of years as well. Fitting models to coastwide data sets has become more feasible than it used to be. Potential applications of the coastwide modeling, of course, modeling the survey data, the index data as a single data set with a model that includes parameters that vary across space. We can still have parameters that differ among regulatory areas, just like we've had before, but they're now part of the same model. We could now model biological data on individual fish, which may have shorter time series, such as the histological modeling data or fecundity data or other biological information, and larger spatial gaps than fish catch rate data. And environmental data collected from our water column profilers, which also maybe have larger gaps as profilers sometimes fail or get lost. And the time series only goes back to 2009. So defining a mesh for the modeling region. So when we're fitting these models in our NLA, we use a set of it involves an approximation using a set of basis functions defined on a triangulated mesh covering the region of interest. And so basically getting at each point on this mesh, you get an exact value, but it's projected elsewhere using a set of basis functions approximating the process. And so our data imply that halibut do not inhabit depths greater than 732 fathoms. at non-negligible densities during the survey period. So we can define a region of interest that doesn't go beyond that, but we also provide an additional buffer, extending it to 800 fathoms and further into Russian waters in the Bering Sea. So that in the past, we've done that to avoid potential for boundary effects at the edge of the sampling region. Other offsets are made, and also it helps, other offsets are made to smooth the edge to avoid narrow inlets. If you have very narrow inlets with these things, the dimensionality of the problem can increase rapidly. If you have, you don't smooth to some degree. It's trying to model, trying to fit mesh points within a very small space. And when you've got smaller spaces, you need more. It's the gem. So we, developing these offsets, we selected values that preserved major islands that make the island shrink to nothing. These for major islands and peninsulas as much as possible to ensure that we don't have non-existent pathways created in the mesh space. In the coarseness of the mesh itself, it defines that the number of vertices allow comprehensive spatial coverage without being so numerous that the model processing becomes prohibitively slow. When I originally did this, I did try various meshes to see how they would work in practice. And something new for this is that we haven't done previously is making use of barrier models. So in recent years, functions in our inlet have been developed to define land and deeper waters as physical barriers, which are used to implement a non-stationary barrier model. This ensures the model's correlation structure cuts off more or less pathways through land, including large islands and peninsulas, along with areas of deeper water that Pacific halibut don't inhabit. Barrier models have a relatively simple basis to them. Essentially, but the theory behind them is actually more rigorous. They're defining the range parameter, which is the parameter, which is under one parameterization of these models, it's defined as the distance at which the correlation becomes between 2 points in space becomes small, which is small. In this case, it's a correlation of around 0.1. And on land, we define that to be a small fraction of the water boundary. So, for example, 10%, and it adds very little computational cost. So the defining of the region that we're modeling over involves creating this mesh. And I talked about the vertices. Those are and it's a triangulated mesh. The vertices are those intersections of the triangles. And the more vertices we have, the greater dimensionality problem, the more time it takes to fit. The fewer you have, the poorer the approximation to. And I know it's hard to see because I've overlaid the survey data on the FIS itself on top, but you can sort of see it in where we have less data. If I say straight up Georgia here, the the triangles are much smaller. There are far more vertices, but they do fill in the space at a reasonable level of approximation relative to the density of the survey and to the strength of the correlation in the models we've had. So. And we extend beyond that space, which I haven't done previously, into the barriers. So we can model into the barriers, but the correlation structure through the barrier model ensures that point here and a point over here in the yellow, their correlation is much weaker than adjacent points on land. So fish can't cross the Alaska Peninsula, they can't cross Kodiak Island, but you see it's actually smaller than the real Kodiak Island because we've smoothed it somewhat to ensure that we don't have such a high dimensional problem in the narrow inlets that we would otherwise have. So this is the smooth version of the coastline. It's the smooth version of the bathymetry, but it's still a good approximation. Preserves the key features of the land masses and islands, while making the dimensionality something we can actually work with. So the application is, in this example that I'm presenting, is to histological maturity data. We've collected these data, and if I misspoke just misspeak, Colin, please correct anything I say. We've collected these data on the FIS since 2022, and Colin has presented as part of the biological ecosystems presentation at the June meeting and previously. Maturity is assessed on individual female Pacific halibut, and each fish has an approximate capture location given by the midpoint of the location of the FIS set. So we have spatially indexed data for each individual fish with the maturity assessment. Recent modeling that we've done so far has modeled the relationship between maturity probability and age and other factors using statistical models that assume each fish is sampled independently, which is not the case. The fish are sampled, there's likely correlation in the probability of maturity in space, and the fact that fish are sampled in clusters on each set. So fish on a set may be similar than fish on different sets, even close in space, relatively close in space, but also you may expect greater correlations in space. Greater correlation of locations closer in space than further. And spatial or spatiotemporal modeling can account for this lack of independence. And this was brought up by Sean also at the last meeting. So this shows the spatial distribution of the sampling up until 2024. We have more samples in 2025 that are not available for modeling yet. Spatial modeling can also account for the gaps, uncertainty due to gaps in coverage, just as it does in the FIS when estimating relationships at biological regions or coastwise. So here we have a large gap for 4B, for example. And when we get previously, when we did a model for 4B, we're basically assuming that the data we've sampled right in the middle of 4B are representative of the entire biological region. And it doesn't account for the uncertainty that we might have in not having any samples from outside that small part of 4B. So at present, we've used generalized additive models to estimate the relationship, but they're more flexibility than the strict logistic model, which is modeling the probability of maturity as linear on the logit scale, but still requires the assumption of independent observations, at least in the versions of the models we've been fitting. To date, I've fitted several spatial models of differing complexity to model relationship and maturity probability and age within the RNLA framework. I fitted the logistic model with fixed effects for intercept and slope, allowing the slope or the intercept to vary, or both, to vary by biological region. So this is mimicking what we've done in the GAM modeling. In the logistic model for that we fitted previously, but with spatially dependent errors with the MET term, which is a pretty flexible covariance function for the error terms. So that's an extension of what we've done previously for logistic models. Logistic models with spatially varying intercept and slope. So rather than just having a single parameter or paraparameters for each biological region, we allow a smooth function that varies in space or time for the slope and the intercept. So fitting the logistic model with parameters for region, it led to very obvious discontinuities at the boundaries because the regions were often quite different as a whole. And so you'd see abrupt changes at the boundaries, which were not biologically realistic. And versions of the model with GAM-like flexibility. I don't yet know how to, I've seen it mentioned in the literature, how to fit an actual GAM model within this framework. I've seen more examples of GAM-like models being fit through this spatiotemporal modeling. And we've done this through a random walk in terms of determining the age relationship. So have the logistic model with a spatially varying intercept and slope, but add a little extra flexibility in the form of that relationship in terms of a deviation from a strict linear model on the logistic scale with a random walk process. And so straight into, I don't give any formula here, but these follow the same models that I fitted previously and have presented previously. They're linear on the logistic scale. We have spatially dependent error structure, and some fixed effects potentially in terms of models for regions in some of the models. But the error structure varies from one model to the next, depending on where modeling the errors or modeling spatially varying intercepts and slopes as random effects, essentially. So here's the output from just the logistic model without the variation for A50, the age at which you expect 50% of the fish to be mature and 50% to be immature. And we can see that the output it's kind of a neat looking figure, but it fits in with the story that we've learned previously from the GAN modeling. Now we have spatial variability in the age of maturity, and it varies across regions. That we have higher A50 values in far south in region 2 than we have in region 3, and higher values also out in region 4 and 4B for the most part. But it tells a more complex story than that. That not only is there variability among regions, but there's variability within regions in terms of the A50. So within region 2, we have higher projected values down in 2A, noting that some of this area has no sampling down in California, forming that, and relatively little sampling elsewhere in 2A. Mid-range values in 2C and 2B, you can see that those orange colors represent something between 11 and 12 in general as an age. Lower values in region 3, but it varies from, say, between 10 and 11 in the east to lower values closer to 8 or 9, the central Gulf, and increasing back up to middling values in 3B, and higher values for 4B and shellfish. Noting again that this region of 4B didn't have any samples contributing to it, though I think there are some samples from 4A. We did have samples in this. So it tells a more nuanced picture than story than the models we've looked at previously. Now here I've extended beyond the mesh, beyond the barriers, outside the barriers, so you can kind of see the effect of the barrier modeling on the output, as well as seeing that how the parameters of the model vary. So in this case, we've moved to the second model I described, which is where the instead of having fixed effects, it's a logistic model, but instead of as was the previous one, but we have random effects for slope and random effects for intercept, and that was the case for the previous model as well. But it's a logistic model without the random walk. And so you can see that the barrier model is creating this well-defined edge right along the contours of the edge of the habitat range. And if I were to strip the land out, you'd see the same thing here. If you go from here to here, these values in 3B are not correlated with values for CDE. So I thought it was kind of neat to see that, but more interestingly is how smooth this process is. The slope varies in a relatively smooth way from southeast to northwest and west. That the rate of change from mature to immature in the curve is much lower in the east than it is in the west. And everything Collins presented previously has backed that up. I think Joseph presented that at the work meeting as well, and made that exact point without this figure, based on previous analyses, that we have a sharper change from mature to immature in the west than we do in the east. And conversely, the intercept, which basically says where the curve is, whether it's on the left or the right, which is not what this figure is. This is the standard deviation, just to show that where we have, as you might expect, where we have greater density of data in the core of the stock, we have more precise estimates. Oh, I thought I had another curve. I don't have the intercept curve, sorry, but it shows the opposite trend, where we have dark colors out east, out west, and light colors. They're basically inverse, negatively correlated with each other, as you might expect. So we can also look at a comparison of maturity curves by location and see how that compares with the GAN model that we previously used, using just parameters that were fixed to region. And here we can have variation within each region. So I have one location within region 2, labeled 1, 3 locations spread throughout region 3, and a pair of locations in region 4. So whereas the GAN model would give the same output for every one of those locations in region 3 and the 2 locations in region 4, the spatial model allows the curves to vary by location. And so this includes the model with a random walk, which is it's a coast-wide term. It's not a term that varies by region. I've tried to fit such a model and I'm having some issues getting that to work. But the dark line here is the output of the modeling that Colin has presented previously for biological region without a year effect in here. This is at the moment, none of these models include temporal fixed effects or autoregressive or temporal correlation. And so we can see general agreement, but there's variation. So here's the region 2. We picked a point that there's similarity between the 3 models here, the spatial logistic and the logistic with random walk. You can see that the random walk model is flattening in between 15, 13, and 20 years of age for region 2, just as it does for the GAN model. So it is taking on some of the, accounting for some of that variation in the curve that we were able to account for in the GAN model. That there's broad agreement between the spatial logistic and the spatial, or very close agreement between those 2 models, except for that flattening effect of the random walk. But we have differences depending on the locations within each region. So in region 3 here, the curves in the 0.2 was in the east of region 3, up below what the GAN model was estimating. We move to the center of the region, and now the curves are above the GAN model, move back to the far west of the region, and they're quite a bit below. So we've got a more localized picture of how these curves vary spatially than we could easily get through just the GAN model. Likewise, in region 4, our understanding of the maturity curve varies within the region. We can build these up into coast-wide maturity curves. When we did this previously with the GAN model, we used the numbers per unit effort, mean numbers per unit effort by biological region from the space-time model as weights to build up a coast-wide curve. Now we can do this at a finer scale. We can use the numbers per unit effort at the station level, and including stations which have no data from the histological sampling, to build up a picture of the coast-wide curve. And you can see none of these curves are very different. It's kind of reassuring that they will come out very similar, but there are slight differences in the logistic model. Again, it doesn't have the flexibility of either the GAN model or the logistic with random walk. The random walk model is able to pull the curve down just in the same way as the GAN model did at younger ages, and flatten the curve somewhat in ages 15 to 20, just as as the influence of region 2 did to the overall GAN curve. But there are some minor differences in the curves. You know that the logistic with random walk model has a discrete look to it, and that's simply the way I projected when you fit the random walk model, you have to bin all the ages. Bin the ages. That's often not enough data, particularly for the youngest and oldest fish, to have to get a good estimate of how the random walk is progressing at those ages. So I created coarser bins than individual years throughout the random walk, and I set it up so that I could potentially do this at the regional level. So they may be coarser. They need to be at the coast-wide level, but I also just projected at those bins rather than intermediate. So you've got a discrete curve there. We can make that smoother. But the interesting is this is how these are the random walk deviations. So these are the variation from the pure logistic model, from the randomized slope and the randomized intercept model. It's saying that just as you would expect, we're expecting lower values for lower probability maturity than just the logistic model. Just as we did for the GAN model for the youngest fish, they go up somewhat here and down again as the flattening of the curve here. So it's basically is in good agreement with what the GAN curve was doing previously, but in a less smooth manner perhaps, but the essence is the same in it. So I think it's doing a nice job of accounting for that non-linearity on the logistic scale that we've seen in the data itself. So there, again, this is preliminary work. There's quite a bit to do remaining. I'd like to look at other options for GAN-like flexibility than the random walk. I'm still see the literature mentioning other options, and I've yet to find an easy way of getting those into the modeling. An obvious step is generalizing the models to include year effects and temporal correlation. Temporal correlation is going to be very important in improving the predictive ability of the models into areas that we're not sampling, and year effects, looking at how these curves evolve through time, which we've seen that they do, not only in the short time series of the histological data, but in the longer time series that you were presented with in June for calibrated visual assessment of maturity. And assessing the fit of the model through cross-validation statistics, the evaluation and comparison. I haven't set that up yet. And of course the big jump would be to apply these models now to the FIS index data. Not ready to do that for this year, but that's where I would like to go next for data that I'm presenting in spatial temporal modeling of the FIS data. Try to integrate it all together in a coast-wide model. It's a much longer time series, even though we're not looking at individual fish as we are with the lost histological data. This is a time series that goes back to 1993. And so we have many thousands of station level pieces of information that we're trying to integrate in this. And so there's a chance. This will take, these models fit within minutes with the columns. But that's not going to be the case for the FIS data.
Even with the barrier.
I don't know that it has. I don't think that has any effect on that. Right? At least the runtimes for these models were similar with I did fit them without the barrier model initially to see barrier model provided a better fit and made more sense. But I haven't yet to try the barrier model for this time. I have a mesh that's only defined on the ocean that they inhabit, so it cuts off at the bathymetry contour and land. So it's doing something to create barriers, not in quite the same way as the barrier.
Yeah, that deep water is the same kind of barrier.
It's not. You can imagine the fish swimming across the water, and so that's one of the reasons that you might advocate for going a little bit deeper than. I don't know how deep. I really don't know how that works in the summertime. The assumption is that they're waters, but
You can potentially get at that with a cost function defined by depth.
Yeah.
Some sort of threshold where the cost is equal to depth down to a certain depth, but then it increases rapidly.
right.
Depth approaching the cost of land at some point.
Yeah, and that could be. That I guess that could work through a barrier model. Has a different correlation penalty for. I'm not sure if that flexibility is. I'll look at that. Yeah. And in this case, I put quite a strong penalty. The authors of the paper were using things like the 10% I mentioned earlier, but these are for the histological data, the processes seem very smooth in space. And so 10% still was quite a large, a relatively small distance in space compared to the breadth of the correlation. So it didn't seem sufficient. So I think I might have put it down to 5%. And that, you sort of figured that to create quite a strong barrier. But anyway, yeah, that's that. I think it's kind of exciting, and it's fun for me to do something new. I think it's a very useful way of looking at histological data in particular. And as we build up a bigger, this year we're going to have more data from 4B. We're going to fill in some other gaps. We don't have a lot of data from 4A previously, so we're building a more complete picture post. So generalizing that to a model with temporal variation and year effects in the parameters. This isn't obvious things.
I'm super excited about this. This is it's such a cool advance.
Yeah, it is.
Yeah, seeing the spatial model with the random effects, it was just like, great, you solved all of the problems together in one model. You don't have to pick, we solved this problem,
Yeah,
but leave the other one out, or
Yeah.
solve this problem. You managed to deal with that that asymmetry
Mhm.
that's really apparent in the data.
Yes. Yeah.
But not allowable with the basic logistic model.
Yeah.
Um,
Yeah.
and while you also account for the autocorrelation there.
Yeah. It's pretty neat.
I was also just really excited about reading that Baca et al. Paper.
Oh, yeah.
My master's thesis was on barrier problems
Oh, it
and
was.
geostatistics.
Interesting.
The run times for the lowest cost path approach that we're using them
Yeah.
is crazy.
Right.
Just the problems.
I mean, their approach is seems so intuitive,
Yeah.
but it's pretty neat. I mean, it was quickly implemented in the software as well.
So that's in our.
It's our inlet, and I guess it has been for at least a few years. But not when I started off.
Yeah.
The paper came out in 2019. I think they worked on the code sometimes.
I've seen people do these models in Gloom TMP as well.
Right.
But I don't think the barrier approach is implemented there.
No, I haven't seen that. Because that's something I've been meaning to look at for a long time. Is the TUB versions of our versions of that, and there are a lot of people, fisheries moving towards using those tools.
Yep.
Rather than say VAST, which I think was the top of this for a long time, but these is from what people have said, a lot easier to use as a novice. The tools that they've got there, and they have most of the features of our own, and some features that our own does not have, such as forgot the term where the correlation varies by duration. What's that called? Thank you. And I yes. So which our own doesn't.
Oh.
No, it's one. And I think back in the day it was one of those things that range and start creating. I found all the threads of him discussing this. How do we? Is this the right way to do this and create his own thing with the way things go? So that's still okay. Which would be a nice feature to have. So yeah. But regardless, this is still a very nice set of tools for exploring patterns.
Thing that's really interesting is that even though we see these grades of a biological parameter, this isn't an implication necessarily of stock structure. These fish potentially moving 1,000 miles to spawn.
Yeah.
And so the fact that you have old, immature fish at the ends of the stock distribution actually makes some sense if you think about most of them going back and spawning in more central areas that they're spending the season.
Yeah, interesting.
So it's kind of mind bending. Usually we would look at this and think, oh, that's kind of stationary biological differences in different areas, but, and some of that may be there for halibut, but some of it's also just where they are when we sample.
Yeah, I mean, the causality is going to reverse there, right?
Right.
You've got maturity driving.
They may be there
Migration.
because they're not mature yet.
Yep.
Exactly. And
Yeah.
and they're also, especially in the southeast side of the stock, they're big for they're heavy for their length, long for their age, and not yet mature. And those are probably all causing each other, right? And then when they mature, now they're making the spawning migration. They're paying the heavier cost of maturity. They're paying the migration costs. We really need a
There's some
conceptual
energetic- I was
model
gonna
to
say,
put it all
yeah,
together.
There's gotta be some energetic conceptual
Right,
theory
exactly.
that sort of defines those trade-offs.
But this is like absolutely the first step to starting to figure out how to set that up.
You know, because when you go through thousands of histology slides, you get a picture in your head over time of like, oh, I'm doing 2C samples, I'm seeing certain trends, but now being able to like visually see it on like a heat map,
Yeah.
it's like mind blowing. Like the first time you showed this to us, I was like, this is amazing. Like,
No, this is, I mean, that's the most sophisticated treatment I've seen of like spatial differences in maturity.
So
Major advance. This is awesome.
next manuscript, right, Colin?
Yeah.
I mean, it's just really amazing to see that advance that the FIS and the spatiotemporal model associated represents taken out to dealing with biological
Mhm.
information.
This is the first time we've tried to do this.
Yeah.
At the individual fish.
So what can the SRB do other than encourage you? on-
I think that's what a lot of people are. I mean, yeah, if you had any suggestions for model variants or things that we were thinking more things already anyway, but I don't. I think we'll work, I mean, we'll be working this up more and have a more fleshed out, ready for, I don't know, implementation, publication type direction. I guess we can present some subsequent meeting.
Yeah, yeah, I definitely encourage you to pursue a publication here. I think that will help in sort of establishing this as a peer-reviewed method. Right now, I mean, for good and bad, it's out at the sort of cutting edge. And I think it will be helpful to have that be peer-reviewed.
Yeah.
Like, yeah, other people have looked at this. So not just the SRB and more limited time that we have, but also peer review publication there. Plus, it's just amazing work and you deserve credit.
We didn't even have the recommendation part of it,
Okay.
but it's in the document. Just noting.
Well, no sign of lunch yet, so you have more to get through for this section. Basha has something in mind for us now?
Just give a quick verbal or just,
I don't have a update on that because we didn't have enough pictures to provide any substantial or present any substantial improvements to the model. And all the other requests, they were more would require additional data. That's why the plan is to provide a full update with the new increased data set, training data set for the next SRB.
Yeah, after lunch, we have half an hour set aside for offline discussion. Ian and Helen both sent out some relevant statements from previous SRB reports. We want to talk about those? Well, what we might do with it. So for example, the one that Ian sent out is what we were just talking about putting potential bias in a value information context. What did they think about that? So this would have been from.
We presented this to you guys last September, and then it went to the commission, primarily at the interim meeting as background material. I don't think that we discussed it as heavily at the annual meeting. We got a polite thank you. But I guess I can't really say we got a lot more than that. It's a long way from, if you had a great survey, you might save yourself $7 million in the long run, to where's the money in October to fund this.
And then the MSE results related to that too. One thing about the assessment analysis of FIST designs and the MSE analysis of FIST designs were that they were both very consistent. If you remember, that was good for us, but your recommendation was to put this into value. So when we presented it to the commission, some of the links that I sent you was like slide 15 of AM 101-12 PowerPoint. That was, we just put at US $6 a pound, the moving from one design to the lower design would result in about a $2.7 million reduction. So we put that into dollar. Yeah.
On average, or just in that one?
On average, the average reduction in TCY based on that FIST design was 450,000 pounds. And at $6 a pound, that's about $2.7 million.
And that's per year, right? That's.
Yep.
I mean, that gets to the questions that they, the ones that Anne Marie brought up that we started discussing, right? What level of precision and accuracy do we need? Fisheries are about making money. So that's just go back and reread some of these things.
The level at which the additional cost is not justified, but additional value of TCUI.
Yeah, and you're a long way from that. Question is, where does the money come from?
Yeah.
And it's up to commissioners to figure that out.
It's a very different way of thinking about what level of precision is needed than other fisheries, I think, because of the value here. Like, yes, this is, on the one hand, you look at these CVs and you think, oh my goodness, most fisheries are managed with much lower CVs, but most fisheries. So there's still value in improving surveys to reduce the CVs here, because they squeeze out of the.
Okay, well, our lunch is here, so let's break now. Come back at 1:30. Somebody join the online.
Well, I think when we come back, we'll be off.
Right.
Off.
Right, so we're done for the day.
Yeah.
For the online version, yeah.
We should close the online